We're grateful and excited to have Charlie Fox with us. I think most of you know Charlie. He's been working in Utah for decades, I think, maybe, with Franklin Electric. So he's well known by a lot of us, has been very involved in the Utah Groundwater Association and in our industry for a very long time, but he's going to be talking about submersible motors, especially magnetic motors, and the new technology that's out with that. So, Charlie, it's yours.
Thank you. So, really quick, I'm going to try to do my best to get us back on track. And I'm really glad that, and Fred, thank you. I'm glad that I don't have to go after lunch. So really quick, as Jim was saying, I'm with Franklin Electric. I've been with Franklin Electric now for 16 years. I cover 6 states in the Western region as a sales regional manager. Prior to Franklin, I was a distributor for 13 years. And prior to that, I was a contractor. I was an installer. So I've been in the water systems business for a very long time. One introduction I would like to make today is we have a new field service engineer that covers Utah for Franklin Electric. His name is Paul Varanges. Paul, would you stand up? If you get time today, meet Paul, get his card. If you have any technical questions or issues or come up with things in the field, that's one really nice thing about Franklin Electric is we are here for you for service and support. So thank you, Paul. Paul's based out of Phoenix, but Utah is one of his states that he covers. I'm originally from Utah, but I live in Idaho. I've just spent the last 16 years in Idaho. All right, so get through with that. Introductions. Today, we're going to talk about something that I'm really passionate about and I'm excited about. I've always been excited about water systems and groundwater. But now I'm really excited for something new in water systems. It's just not the same old thing anymore. So when new things like this and opportunities come up, it's great to work for a company who's on the leading edge of that. Research and development has been key for Franklin. So today we're going to talk about efficiency and permanent magnet motors. I'm kind of a guy that I use some of those smart devices, right? So I might ask my Alexa device how to spell something or what the definition of something is. So if you were to ask Alexa, what's the definition of efficiency, you're going to get 2 main ones. And so the first one is the ratio of work done or energy developed by a machine, etc., to the energy supplied to it, usually expressed in a percentage. The next one I want you guys to remember, not that the first one's not important, but that's going to kind of draw in key to everything that we discuss here today, but is also the accomplishment or the ability to accomplish a job with minimum expenditure of time and effort. Because I believe that's even bigger key than just the efficiency goal, right? That's another part of efficiency that we really need to pay attention to. So if you ask that and you look at some of those definitions, I want you guys to think about your microwave in the house, right? The microwave uses 50% less energy compared to baking or cooking something in your oven. And then that's even increased if it's summertime, right? If it's 90 degrees or 100 degrees outside, what's going to happen if you cook in your oven all day? You're even going to become less efficient because what else is going to run? Your air conditioning, HVAC, right? And so the other one to look at efficiency too is, so the microwave is very efficient. The other way to look at it too is every time, and my mother knew this, by the way, every time you open the refrigerator door, you lose 30% of the cold air. It escapes. So now that refrigerator just became inefficient, right? Another way to look at efficiency is I own 2 Ford trucks. One is a little Ford Ranger with a 4-cylinder engine. It's very compact, small, easy to get around in. The other is a 2002 7.3 Power Stroke 4-door, 1-ton dually, okay? Am I going to be efficient if my wife asks me to run to the grocery store and I jump in my dually? Probably not. Number one, it's going to cost me more money than it's costing that little truck, right? Because fuel expense. Number two, how long am I going to take driving around looking for a parking spot? And the industry that we're in, you guys all understand that, right? I'm sure that.
How fun is that going to be?
Well, yeah, exactly. I'm sure there's been more than one time that you've stopped at the grocery store in a drill rig. It happens, right? Okay, so those are just a couple examples. But I definitely want you guys to remember number two. So why is efficiency so important? Here are the top reasons that it's important in our industry, the groundwater industry. Number one, our resources are being stretched, creating a higher demand for efficient equipment. Number two is efficiency is becoming extremely important in water management. And the third, to me, is the largest, and that's the financial benefit. So those are the top three, why it's so important in our industry. When we think about efficiency related to pumping systems, here are a few challenges that we're faced today, right? We've got an aging infrastructure. So that would be not just the power grids that we're dealing with that supply us the energy, electricity that we need, but also it could be things in the actual water system itself, some aging components, right? Piping that's degraded, different things like that. And then more power consumption is being used, more water is being used, and there's more of a need for water conservation now, and more regulations being put on us. So when we look at what's going on and what's causing all of this this infrastructure strain, if you were to look at the state of Utah here, you're going to see that big giant red mark, right? Well, that's drought. And although we just had the best winter that we've had in 20 years, right? We are still probably going to take 5 to 7 of those same type of consecutive years of those types of winter before we're even out of this red spot. The other problem that we're seeing is people moving from other states into our states. I happen to live in Idaho. I can say, yes, it's happening. And you live in Utah, and I know that you've felt it and seen it too, right? So with that, it is just requiring more power, more water, and people are moving out of places that might have had water. Now they're moving into places where there's less, and we see more and more, right? So what happens when all of that goes on, right? Everything that gets a higher load rate on it, especially utilities, the price for power goes up, okay? And not only that, but governments get involved. And I can tell you that there's already some involvement there. I just want you to pay attention to what's listed under the U.S. So in 2020, there was what we called the Department of Energy Pump Efficiency Standard. Okay, and basically the Department of Energy put out a deal to every single pump manufacturer and said, if your pumps don't meet this efficiency range, right, after a certain date in January 2020, you can no longer produce that. Now, it didn't affect a contractor or a distributor who already had that product, but it affected the manufacturers. So I can tell you that one thing that Franklin looked at and did was not only did we meet those standards, but we exceeded those standards. And so everyone had to start putting what they call a pump efficiency index on every single product that's out there. And then we saw it before that with, like, say, surface pumps. And that's why premium efficiency became so important in the surface pump world. Yes?
So how did you do? You just make the windings tighter? Or?
I'll get to that.
Oh, okay.
Yep. So basically, all of these regulations that are being put on us, right, This list is just going to grow, and the demand for more efficient pumping products is just going to increase. We won't see that decrease ever. So if we look at a typical submersible well, one thing that I just want to really point out here, for years, the pump has been the focus for increasing efficiency, right? And there's these 4 things that we've done. We can adjust the speed of the pump, modify the impeller trim, change the number of stages, or change the pump design completely. In the fact where Franklin got involved in we were always a submersible motor manufacturer, right? Franklin's getting ready to celebrate, 80 years in the industry. And so we understood and knew submersible motors. And for years, we were making our motors for other pump manufacturers. And when Franklin decided to get into the pump business, we understood that there was a need for an efficient 4-inch pump. So I want you guys to think about something. A standard 4-inch pump for years, the standard hydraulic design, is what we call a pancake style impeller. It's flat across the top and straight flat across the edges. So I want you guys to think about something. As that water comes through the suction of the pump, the first thing it's doing when it goes through the eye of the impeller is takes a 90-degree turn. As it exits to go to the next impeller and the next stage, another 90-degree turn. When you continually do that and you have a high stack rate, and to get water to the surface and to build pressure, right, you just continue to increase stages, okay? And with all of those 90-degree turns, that 4-inch pump with that flat pancake impeller becomes very inefficient. In fact, you would be surprised if you looked at some of those curves when you looked at the efficiency curve. So now another pump design that I want you guys to think about is how a turbine pump is built, okay? And think about that impeller design, or even the bowl design, right? So that impeller is not flat across the top, it is concaved. And if you look at the edges, they're not straight off. They're what we call scalloped, right? And so if you look at the round bowl design, so as that water comes through the suction of a turbine pump, it is now making this type of a transition, okay, instead of all of those 90-degree curves, turns. And so what does that do? That increases the efficiency. A turbine-style impeller is very efficient. So back around in the late 90s through about 2003, Franklin was working on developing what we call our own hydraulic design, and it is a radial turbine design impeller. And so if a lot of you in this room are familiar with what Franklin calls the tri-seal, that tri-seal hydraulic is actually a radial turbine design impeller. One of the benefits that it gave us was we can now build that pump to do the same job and probably even a little better performance with less stages. And the first thing when I tell everyone that is, well, okay, so you're giving us less stages, that means the pump's going to cost a little less, right? Well, Franklin took everything that we saved out of decreasing those stages and put it right back into that pump. So you get a stainless steel suction screen, you get a VFD check valve in the top of that pump, and we use Celcon material for all our impellers. We don't use Lexan, we use a material called Celcon, and it's industrial grade, very heavy duty. The other thing that we do to give that pump its strength against abrasives and temperature is we glass fill the Norel product. And we glass fill ours to 30%, where some other manufacturers are about 20% in the industry.
What are you glass filling?
The Norel product that the stages themselves are made out of. So that's a process when we manufacture that. So ours are glass filled to 30% versus some in the industry that use 20.
I guess I don't know enough about, why does that make a difference?
I'm not gonna lie, that is way over my head as far as how that process goes, but I can say that it makes a difference in the temperatures that it can handle. It makes a difference in abrasives that go through the pump, how well it handles that and stands up to that. Yeah, exactly. The glass filling is what gives it its abrasive resistance and temperature resistance.
It makes it tougher. Okay.
Exactly.
So on your different stages in this radio, it would seem like there's only two things if they're all hooked up to the same motor, turning the same speed. So the only two things you could change would be the tilt on your blade, or the spacing, how many of them there were in each stage.
Correct.
And you would seem like you'd need to change that as you went up the stack, so that each one is able to pull apply some more pressure from the one below.
Actually, all of those impellers in, say, our 4-inch. Now there are some turbine designs, but we only change those when we're looking at horsepower, right? So when we start to trim those and change impeller sizes, we only do that in, say, very large turbines. We don't do that in our 4-inch product. So
they would all be the same,
all the impellers are identical.
identical all the way up the stack.
Correct.
Okay.
But the higher efficiency becomes from the actual impeller design, being a radial turbine design versus what we consider inefficient flat pancake design.
Pushing up instead of out.
Correct. So if you think about that what has changed there with the pump over the years, what hasn't changed? So there's the pump. The motor hasn't changed for years. Like I said, Franklin's going on being a motor manufacturer for almost 80 years now. And Franklin actually came out with the very first encapsulated 4-inch motor for wells. We didn't invent the very first submersible motor for wells, but the first encapsulated winding was from Franklin Electric. So there hasn't been many changes as far as the motor go, right? So when we look at a submersible motor, I only really want you to remember two things about the design. And that is that the rotor rotates and the stator stays stationary, okay? And I'm going to jump through some of these quickly so that we can stay on track. So when I talked about in an induction motor, that the rotor rotates and the stator stays stationary, I want you guys to think about how this works. We actually apply current to the stator, and the current is what turns and goes around the stator, right? That then is transferred to the rotor and creates a magnetic field, okay? Then that rotor starts to turn. But I want to tell you why an induction motor is not very efficient. And that's because there's losses in that process. So as we're doing and creating that magnetic field and forcing that rotor to run, we actually have some losses in that. And in the submersible motor world, we call those losses slip. And so if you were to open up a pump curve, 90% of the pump curves that you're going to look at today are all probably 3450 RPM, not 3600 RPM. 3450 is in relation to what goes on when we have that what we call slip. Okay, so here's kind of a visual of an induction motor. The green portion being the rotor, the blue being the stator. We apply that. The current, which is in the red, starts to go around. But as you notice, the rotor does not turn at the same speed. Okay, so think of it as a dog always trying to catch its tail, turning in a circle. And here's what that looks like, because remember, I did say that the stator was stationary. So this just kind of shows that current moving around the stator, and then the rotor following it. But it's not synchronous.
It looks like they're going the same speed, it just is lagging.
They are, so you're correct. It does lag behind. It's not a true synchronous motor. It's what we would consider asynchronous.
So if you had them walked up, then that would be more efficient?
The less load you have, the closer it gets to synchronous speed. So at 3450 at full load, at no load, it's gonna be running at 3550. So it'll run 100 RPM faster at no load, because it doesn't have the, torque is developed by this thing called slip. And the farther the electric field is behind, the more torque it develops.
Well, the more electricity it's going to use too.
Sure.
Okay, all right.
So one thing that I really want to point out here, and I want everyone to walk out of this room and remember, that we didn't just go out and create a whole brand new motor design, okay? The only thing that changed in the Franklin electric motor, submersible motor that you know today is the rotor. We took the copper bars out. So if you see in this picture, all the way over here to the right, you're going to see the copper bars, right? So we took those out of the rotor and we put in rare earth permanent magnets. That's it. The sealing system stayed the same. Your thrust bearing system stayed the same. The way that we encapsulate the windings, right? Everything else, the material on the shell of the motor, the whole 9 yards, the way that we do the shaft, everything is still the same. The only change is we took out the copper and we replaced it with magnets. So what did that give us? Well, now we don't have to create that magnetic field, right? We don't have to take that current that's applied to that stator and those losses that go to that rotor, right? We've captured all of those losses, and now with this design, as you can see, we've got an example of an induction motor and a permanent magnet motor. And you're going to see that the permanent magnet motor is a true synchronous design.
Is that just because it's instead of dragging it, having to induce the field, and so there's some lag there, and that's why it's dragging it on the other side? The
Well,
magnets you've got in the rotor are actually, they're pulling too?
Magnetic field it is more uniform, so you're not getting the lag.
yeah, correct. And see, this is why I'm really glad that I brought Paul with me.
You don't have to energize, you don't have to induce the current any longer because the magnetic field is there in the rare earth.
And thank you, Paul.
You're ready to go at start.
So basically, we have taken away having to put that extra current into that stator and transfer that to the rotor. It's already in the rotor. Those magnets are already there.
So it runs 150 RPM faster. Yeah, it does.
It has the ability to run that, yes. And I'm gonna tell you why we don't run it right there out of the gate in a couple more slides. But thank you, Kyle. Yes.
A true synchronous motor runs at 2-pole speed, which is 3,600 RPM.
You are correct. You are correct. And that's also an advantage with a permanent magnet motor, and I'll show you why. So when we look at what we actually gained, okay, we got to keep a couple of things in mind here. That remember I said we have the same bearing system, okay? We have the same sealing system. So basically, we have the same friction losses as we did with an induction motor. But where we really gain that is now we have no electrical losses. So if we look at how does that really, what does that do? Okay, how much more efficient is the permanent magnet motor than an induction motor? So we've kind of made up this chart that shows 4-inch through 10-inch. And yes, by the way, we are making this through 500 horsepower today. If anybody wants to order a 500, I'm taking orders today, and I'll probably give you a little bit of a discount. Just one day only for the Utah Department of Water Resources training. Okay, so if you look at this, everything in the green is what you gain from everything in the blue is what a standard induction motor is, and this chart is efficiency, okay? So the biggest gain, if you look at the 4-inch, would be a 5 horsepower. An induction motor is 78% efficient. Permanent magnet is 90%. If you go over and look at the 6-inch and go to the 60 horsepower line, a 6-inch induction motor is 84% efficient. Permanent magnet is 92. So what does that mean? It means that there's up to 12 points, 21% improved efficiency by using a permanent magnet motor. And by the way, to Kyle's point, that is compared to a standard induction motor construction at 3450 RPM. This motor has the capability to run to 3600, and I'll talk about that too.
Are those all on the top of that small one? I noticed that it goes up and then it's back down as you get, say, from 8 to 10 horsepower. Do they all do that if you ran it out a little ways? Is that why, that's why you're going to a larger motor, or is it just to fit a larger hole?
Because you're squeezing 10 horsepower out of a 2-inch diameter rotor and a 3 3/4-inch diameter casing. And that's really hard to do, so that's why the efficiency dips at the top end.
The bigger motors are just
The motors are only this big around. You're getting 10 horsepower, the rotors, that big around. And that's why that efficiency goes down, because it's almost an impossible task.
Okay.
Right,
But
Charlie?
You're correct.
Okay.
Hey, why having T-frame motors? Why don't, we haven't seen any permanent magnet T-frame motors?
It's coming.
Did you guys really start this design?
So Franklin, and this is a perfect slide to explain this. So permanent magnet motors are nothing new, okay? Most of the appliances in your home, dishwasher, washing machine, refrigerator, your computer drive motor, swimming pool pumps, it's huge. In fact, in the state of California, you probably can't buy a swimming pool with an induction motor. Their regulations all say that they have to be permanent magnet. Electric vehicles, most of your hand tools. So permanent magnet motors have been around for a very long time. Franklin has been building permanent magnet motors for years. In fact, for one of our competitors, we manufactured their permanent magnet motor for about 10 years. In Europe, this is our 4-inch permanent magnet motor is our most popular motor in Europe, and that's all due to regulations. So we've been doing this for a long time. I'm not going to say a very long time, not 30 years, right? But 10 years plus. John, you had a question?
But what rare earth, are the rare earth minerals you mentioned in there, are they the magnets?
Yes, rare earth magnets.
Where is that coming from?
You know, that is
I
it.
never would have asked before the pandemic, but the supply chain got screwed up. And I know most rare earth stuff comes from China, so.
So most of
In the weeds when the supply chain breaks down?
Most of that is European. And I will tell you this, that is also in Europe is where our manufacturing facility is today for permanent magnet motors. Yes.
Looking at the different designs, it occurs to me that you've got a third design that you haven't talked about, because it's not going to be useful submersible, but that's a brushed motor like you have on a starter in your car. You can't use it underwater because how are you going to, when you wear out your brushes, you're done. But you could use it on surface, but you didn't discuss that. I was
Typically
wondering.
DC.
DC only?
Yeah, DC only. Brush motors are DC.
Yeah, okay, but it's
You
not hard
can't
to
run
convert from
you
AC.
can't run a submersible motor on DC.
Why not?
It was spin back and forth, so you start doing that.
Sorry, I didn't understand.
Yes.
You guys are secure with just long-term where that's the manufacturer?
Most definitely. Most definitely. Yes.
It starts to spin and that current's going a certain direction, but DC doesn't go in one direction.
Right. But it
DC motors are way less efficient.
is
locomotives now, they're changing locomotives from DC traction motors to AC variable speed motors.
Could you imagine if we could do locomotive engines with permanent magnet?
Well, so my question is, if you, with a brushed motor, what does it look like in terms of the lag? Because you're not gonna have that same lag that you have where you're trying to induce a current in your rotor and then drag it along. That's the advantage it looks like you have with the permanent magnets, is that you're not trying to induce a current and then drag it. You've got two magnetic fields and they're attracted.
Paul, do you have any input on that question?
And it seemed like you could do the same thing if you have brushes. Because you're not trying to induce, you're not introducing that extra inefficiency of trying to create that second magnetic field.
Good question.
Electricity's already there.
Well, it would work the same way, but you can generate much more power and torque with the AC motors. I guess in principle, yeah, it would perform the same way as a permanent magnet theoretically, but as a practical matter, I don't know if that would work.
Well, the alternator in your car is an AC generator, and the only reason you get DC out of it is because you're running it through diodes to flip half of the signal over.
You can do that, but I don't know if pound for pound, you're getting the same delivery of power out of a brushless as you would out of a permanent magnet. That I can't.
Oh, okay, I just wondered if you knew, yeah, all right.
Okay. So, moving on. One thing that I do want to touch on is all permanent magnet motors. I don't know of any that exist today that do not require a VFD to operate. And I will quickly tell you why that is, and then we'll talk about VFDs for just a minute. Okay, so what needs to happen with the permanent magnet motor is the rotor fields of a permanent magnet motor always need to be aligned. The VFD does that, okay? The other thing, we talked about being able to run at 3,600 RPM, right? And also, another feature that we use, like in the sub-drive world, where we're mix matching motor horsepowers and we're running above a certain hertz, right? We're never overloading the motor. We're never even running into service factor when we do that. But we do need the ability with the drive to be able to run above that speed, right? And that's another thing that the drive gives us that it can do. So the drive helps keep the rotor and stator aligned and allows the motor to run above power line frequency. And to point out at the very bottom of that, 115 hertz is 3,450 RPM, and 120 hertz is 3,600 RPM. Now, when you guys are using these and setting them up, say with a subdrive, and you see that it's running at 140 hertz, I don't want anyone to freak out and go, man, I'm turning at 8 or 10,000 RPM, right? Not the case. At 120 hertz, you're only turning 3,600. At 115 hertz, you're turning 3,450. So keep that in mind. And one thing that I didn't say is that permanent magnet motors also, all that I know of, are also 4-pole motors, and that's why we have the 120 hertz.
So is VFD, is that like variable?
Variable frequency drive.
Okay.
Now, keep in mind that I did say that it takes a VFD to operate a permanent magnet motor, but you want to make sure that your VFD has the capability of doing it. So one thing, just to make this pretty short and sweet, if it were me and I was a contractor and I was going to be installing a permanent magnet motor, I would buy it as a package. Okay, I would buy the manufacturer's VFD that is probably already programmed to run a permanent magnet motor. I don't want to just go pull something off the shelf or something that's existing and then have to go through all that programming, and here's what that looks like. This is the simplified programming on option 1 if you were just setting up a VFD to run a motor, right? These are the normal things that you're going to be telling the drive to set it up. Here's for permanent magnet. I ran out of room, okay? There's like 22 things on there, and I can tell you also, if you were to call the manufacturer to ask for some of these things, they would probably go, what are you talking about? I don't know that information. We're going to have to get with our engineers. So if you buy a permanent magnet motor system, just buy it. Doesn't matter who the manufacturer is, just buy it as a package system. Buy the drive and the motor together. That way you know they're working together, and they're probably 90% already programmed for you, as you saw in option 1. We won't spend a whole lot of time talking about benefits of a VFD because most of you in the room already know that. But what we will talk about is how to explain that to an end user, okay? So we all know and understand that the VFDs can soft start a motor. They can prevent water hammer. They can provide us constant pressure, which is probably 99% of what your customers are looking for, right? And it can also give us the ability to convert phase. So single phase to 3-phase. That's all achievable by using a VFD. But sometimes it's really hard to express that to an end user. So maybe sometimes we go about it as talking about something that they do know and understand, okay? So when we talk about varying the speed of the motor as far as RPM goes and horsepower goes, we could probably relate that to their car. So I want you guys to remember this. So you would tell them, do you ever use cruise control in your car? Oh, yes, all the time. Okay, so you're going down the highway, right? And you're doing 60 miles an hour. You're on flat ground. You're in overdrive, right? Your RPMs are low. Your horsepower draw on the motor is low, okay? And you're in cruise control. Pretty economical, right? You're saving, you're getting great mileage. Everything's good. But you crest a hill. You start to go up a hill, right? What happens? Your car might downshift, okay? Your RPMs go up. What happens to your horsepower? You start demanding more horsepower out of the engine to get that done. Okay, what hasn't changed? 60 miles an hour, okay? Put that in relation to running their system at 60 PSI. Now you get to the top of the hill and you're coming down the backside. What happens? Right, your RPMs drop, your horsepower load way decreases, but what stays the same? 60 miles an hour. So that's probably the easiest way that I know of to let someone know how this is in relation to the motor, the speed, the horsepower, and the demand that's put on it. One other thing that you get with permanent magnet motors is a higher starting torque. And a couple of things that I can tell you where that might come into play and be helpful is, let's say, a cabin well, and it's sat for months and months and months without being ran. Impellers could start to get a little iron fouled. You could have some debris built up in there. And if you're on a VFD and it goes to start, what could happen?
Blocked rotor.
Yeah, you're right. You're right. It could pull higher amps and the drive would kick out and try to protect it. In some cases, when I get those calls, and maybe even Paul gets those calls on troubleshooting, it's a 3-phase motor. So we might just have you swap the leads on the outside and bump it backwards for a minute and hopefully break it up enough, whatever's settled inside of those impellers, and then start and run. But with a permanent magnet motor out of the box, you're going to get higher starting torque. So that might be a benefit. So the other benefit, I'm going to tell you right now, in our 4-inch, our 2 and our 3 horsepower are the same part number, right? So when you open and take that out of the box, it's going to have a rating on it for a 2 and a 3 horsepower. But when we look at our 6-inch product line, and this is just a demonstration of a This isn't a pump curve. This is a motor speed and efficiency curve with horsepowers. There's a 20 horsepower induction. There's a 25. And there's a 30. All three of these motors are covered with one induction motor. So in the case of our 6-inch motors, instead of stocking 9 motors at your distributor, they're now going to stock 3. So one motor can cover 7.5 through 15 horse, the other 20 through 30, and the third 40 through 60. So only 3 motors is going to take to cover 9 ranges. There's another huge savings on cost for wire. Up to 22% longer wire runs per wire size, per horsepower, okay? That's pretty huge. Let me show you just an example. With this example, I used a 60 horsepower, and I made this chart up last year. So a 60 horsepower, 6-inch motor is rated at 92.3 service factor amps, okay? It's going to require number 3 wire at 550 feet. So if you look at a permanent magnet motor, it's only going to draw 80 amps, and you could use number 4 wire. So in this application with 550 feet, you would have saved the end user $822 in wire.
No. That's $822 more in your pocket.
Hey, any way you want to work it, Kyle.
Why would you give the customer back that?
Well, there you go. Do with it what you may. All right, so not only that, who would much rather be installing smaller wire? Me, right? Here's another thing that's pretty cool. The size of these motors. I actually brought one, but then I realized that I grabbed the induction motor out of my truck and I wasn't going back out. So the size is considerably less. We're going to be 40 to 60% less in length, not diameter, in length and weight by using a permanent magnet. Okay, so in this chart right here, if you were to look at, we use a 60 horse as an example, but all of them pretty much follow this same thing, right? So a 60 horsepower induction motor weighs 298 pounds and is 61.3 inches long. And permanent magnet motor, sorry, that was an induction motor unless I didn't say that. A permanent magnet motor is only 40 inches long and weighs 172 pounds. So would you rather install a 172-pound motor or a 300-pound motor? It might even make a difference on what rig you drive that day, right? Might even make a big difference in what pipe you put down the well. Okay, we've had some cases with some really deep sets on 4-inch where the guy said, I hate using galvanized, but I have to because, you know, this is a 5 horsepower motor. Well, look at the difference in this chart. A induction 5 horse weighs 50 pounds. A permanent magnet weighs 32 pounds. So pretty big difference when we start hanging that thing at, say, 600 to 800 feet. It does make a difference. And once again, makes a difference for you. Remember I told you to remember that number 2 accomplishment, right, for efficiency? And that becomes, you become efficient. Your time and your effort. Who uses pipe wrenches? Come on, everyone. You all use pipe wrenches, right? Who has aluminum pipe wrenches? Why? Takes a lot less energy to use that aluminum pipe wrench, right? You can run that thing all day compared to a 36-inch rigid, you know, so it does make a difference. The other big thing that engineers have looked at for a very long time is a submersible motor was not efficient, and we all know that because I proved it with the induction motor, right? It's not as efficient as, say, a line shaft turbine until now. So if you look at that chart, a line shaft turbine is 90% efficient. Well, now our submersibles are 90% efficient, so we've matched that. And in some cases, there's a big benefit to using a submersible. There's fewer parts, less time to install it. There's a reduction in overall size and weight, and it's quieter. If you're putting it next to a subdivision, nobody's going to want to hear that line shaft turbine motor run all night when you're doing your pressurized irrigation. They won't hear the submersible at all.
Well, so you're on the right there, that is a brushed motor.
No, it's not.
It's not?
Nope. It's a squirrel cage induction motor.
It is.
Oh, it's still induction, okay.
So we talked about the fact that this can run at 3,600 RPM and the benefits of that. I wouldn't go out and set up every single system to run at 3,600 RPM because there's a good chance, per the pump curves that we have today, that we could overload that motor, right? But where might it give us some benefit down the road to be able to go to 3,600 RPM? And I'll give you a scenario. Okay, in the middle of Idaho, there's a pivot. Okay, there's a 15 horsepower pump that supplies water to that. There's 2 months left in the irrigation season, and that 15 horsepower pump is worn out. And it can no longer meet the demand at 3,450 RPM. But we go out and we bump that up to 3,600 and cross our fingers, and now it's able to meet and build the pressure and meet the demand, and it might get them through the next 2 months without having to, have somebody out there overnight swapping it all out or be on a 6-week waiting list for a component and not be able to finish the irrigation system and possibly even lose a crop. There's one benefit to being able to run at 3,600 RPM in my mind. I wouldn't size everything for 3,600 RPM if I was doing it today. So the ability to run at 3,600 versus 3,450, if we stayed at the same head pressure, but we just increase the flow, we can increase that 10%. If we did the opposite, we stayed at the same flow, but increased the head, we could increase that by 14%. Just by going to 3,600 RPM. Cost savings is huge. This is just a graph that shows motor savings, 4-inch through 300 horsepower. So if you look at that, there's some considerable savings, right? If you were talking to a dairyman who had a 40 horsepower system, maybe even a 15 or a 20 or a 60 horse, I'll show you what that looks like. So this is a 15 horsepower application. It's for a dairy. It runs 24 hours a day, 365 days a year because you guys love milk. They're paying 10 cents per kilowatt hour, and here are the savings. An induction motor would have cost them $13,841. The permanent magnet cost them $12,264 to operate in a year. So that dairyman saved $1,577 by going permanent magnet. Same scenario for a 60 horse. Now he saved $4,783. Okay? Now we'll get huge. And I know this is a really hard chart for you guys to see, but this is a 250 horsepower municipality. Okay, submersible motor. I won't get into all the duty cycles and everything else in this one, but I will point out the price difference. So if you look at what they paid for a permanent magnet system, motor and drive, and this is list price, right? That was $138,000, okay? An induction motor would have cost them $130,000. So there's an $8,000 difference. But in the first year, we're able to show this municipality that they could save $9,791 on power. So that more than paid within the first year for that system to be upgraded to permanent magnet. We say 1 to 2 year payback on these systems that use a lot of water, that run a lot. If it ran for 10 years, these guys are going to save $100,000. And what's not changing? The price that we're paying for our power. It's never going to go away. It's never going to go down. The big picture is what this really costs you throughout its life cycle. Same thing with your car, right? How much does it cost you, not the initial purchase price, but to operate that car? The oil changes, the tires, the maintenance, right? All of that. So if you look at a water system, your initial purchase price is only 5% of what the life cycle of owning that water system is going to cost you. Another 5% for maintenance, right? But what's the big picture here? 90% in energy. So if the end user looks at that, it's going to be a no-brainer when they think about what motor they're going to put in. More runtime, more payback. Okay, I said 1 to 2 years, and we haven't seen much over a year that it takes for them to pay back in those systems. Huge savings. So these are the applications: commercial, ag, residential, of course, dewatering, mining, and then groundwater remediation. So we get asked a lot of questions about this, right? Does high efficiency mean that the PM motors run cooler than induction motors? No, they do not. Now, if they were the same length and had that same cooling flow, then yes, we would say there's probably a huge advantage to going to a permanent magnet for cooling, right? But they're rated the exact same. Most of your 4-inch motors are rated at 86 degrees. Same thing here. What troubleshooting is different in a permanent magnet versus an induction motor? Nothing's different. You do it all the same. You use your megger the same, you use your meters exactly the same. We talked about the difference between the 120 hertz versus 60 because this is a 4-pole motor. And it does run at 120 for 3,600 RPM. Then why does it turn rough by hand? And this is where I really meant to bring one. So as you rotate, who installs 4-inch motors in the room? Okay, what's the first thing you do before you couple it to a pump? Turn the shaft, right? Turn the shaft. And you're going to notice that the first time you grab a permanent magnet motor and you turn that shaft, it's not going to feel the same as the induction motor. Even though it has the same thrust bearing, you're going to feel those segments of those magnets as that rotor turns. So you actually feel some resistance there. Does not mean that you have a bad thrust bearing. It does not mean that you can't put that motor down the hole. Somebody asked about temperature with the magnets, or you didn't ask about temperature. You said, do they ever lose? The question was, do they ever lose the what's the word for I'm looking for, Paul? There you go. Thank you. Thank you. So, what will kill a magnet? Temperature. Okay? So that throws up a red flag, right? Well, we know that this is an electrical motor. It sees temperature, okay? I can tell you this, from all of our studies that we've done, you would actually cook the windings. You could possibly melt the insulation off of the wire before you would damage the magnets in this motor, okay? So running at higher temperatures will not be a problem. Guarantee you the motor would fail way before otherwise than it would because it had a magnet in it. All right, so really quick, some key takeaways. Lower energy consumption, reduced operating cost, compact design, return on your investment, built together to work together, inventory management, And what we're all looking for is the reduced footprint. So return on investment, Kyle's customers aren't getting any of that. I'm just kidding. They're, of course, getting it because they're going to pay, when he puts in his first 250 horsepower motor, right, they're going to pay around $9,000 to $10,000 less annually to run that motor.
But they're getting Kyle.
They're getting Kyle. And
I need a 450 today, you gonna discount that a bunch?
you bet.
You said half price.
You bet. Do I have any distributors in the room? Okay. So I know that we probably ran a little longer than what we should, and we have a lot of questions. I'm going to give you guys a really cool tool right now, and I am going to share this with you because I'm going to tell you this right now, and this is wholeheartedly. If you install Franklin products, I am part of your team. If you call me Friday night, if you call me Saturday morning, I know when I see that you're calling me, I know that you're in front of a system and your customers without water, right? And if I can, I'm going to answer. So if you're stuck, I'm stuck. We're in this together. I'm just part of your team. So please take my information. That is my cell phone number. That is my email address. And that website has more information on Franklin products than you'll probably ever want to know. Thank you.